Alright, hello, it's time for another Physics Teachers Are Awesome reaction video. Today we have inclined planes. Let's get to it.
All right, in this problem, oh my goodness, in this video, we're going to talk about inclined planes or ramp problems. So we're going to start off with you guys kind of doing some ranking on your own. So let's say we have.
So this looks like OneNote. Yep, it's OneNote, definitely. And I talked about in another video how OneNote doesn't really have pressure sensitivity in that the ink actually goes grayer, but you can see that it gets skinnier, and I think this is super awesome. Did you also notice that she was doing a little bit of zooming? That was pretty cool. So she's able to make it exactly, the size that she needs it to be. So far so good. And I'm thinking maybe this is the first time they have done these inclined plane problems. I think what's interesting about these four is that these three, well, this one makes sense onto its own. They've probably been doing that problem for a while. These two make sense. And then this one is weird, right? So this one is different because I think the students would think that the ramp doesn't matter at all. And so I don't know if students would call that a ramp problem. So I'm really excited to see how she goes about doing this, and notice that she's about to do a ranking task, which is super awesome.
Frictionless surfaces, and we have these four situations where we have a block of the same mass on some different surfaces. So A is completely horizontal, D is completely vertical, and then B and C are at angles where C is a little bit steeper than B.
It's interesting that only in the last couple of years have I realized that horizontal and vertical only make sense when there's gravity. So of course, all of our students' experience is with gravity, and so we tend not to have to talk about it very much. But I was doing some problems where I hadn't bothered to turn on gravity, and I was using the phrase vertical. And I realized, wait a minute, that actually doesn't make sense. And we think about how science fiction movies get that wrong all the time. Well, don't get it wrong so much as it seems like all of the ships in Star Trek and Star Wars have the same definition of vertical, which is sort of the vertical of the camera. And so I think it'll be curious to see when she says the word gravity.
So what I want you guys to do is to think about how could we rank the acceleration of these objects, and how could we rank the net force of these objects? So go ahead and pause the video and go ahead and take like a minute or 30 seconds or so to do that.
So this prompt to, hey, pause the video and think about this for a second. It's so hard to know if students do it. It's interesting how you would develop a culture with your students to say, look, this is going to be worth your while to put some time and thought into this. But you know that there's students who just blow right through that, say, yeah, I know you're about to tell me. So I think that it's really, really hard to try to find ways to make things whose educational value are dependent upon students making choices that they might not make. And so I would really love to know how she sort of fosters that culture for them to pay attention to prompts like that. Oops. Oh, she's quiet for a minute.
So hopefully you have some rankings down. You paused the videos. You did what I asked you to do. And your ranking for acceleration should look something like D. So I should probably say that I'm going from greatest to least. Right? D, C, B, A. Okay. So A, because there's no net force, we can recognize that A has 0 acceleration. And D, well, D is just going to fall straight down, which means D is probably in free fall. So D likely has an acceleration equal to G. C has something a little bit less than G, and then B is something a little bit less.
Still hasn't said gravity.
Now your net force ranking is likely going to look exactly the same because we have the same mass for each of these. Okay? Our net force is going to look like D.
Did you see that? She was able to talk while correcting her writing. That's actually really hard to do. So she had misspelled least, and she kept talking while she corrected the spelling of the word least. What's interesting about that is, number one, that's amazing. I mean, that's really hard to do. Number two, the question is, would the students have been paying attention to that, or would the students have been listening? How does the audience react to what, frankly, is an amazing demonstration of I know people hate this word, multitasking. I also think it's interesting how OneNote doesn't let you see the mouse until you're writing. And so what typically will happen is you're standing there waving your chalk and you can sort of get them to pay attention to your face. And we all know that adding the video to these adding your face to these videos, like I'm doing right now, adds a ton to the file size, right? So every time I upload these, it takes forever. And when I ever do a video where all I do is record my screen, boom, it's like this teeny tiny file, upload it, no problem at all. And so there's a cost to adding something where you can say, hey, look at me now, look at me now. In fact, you know that I could actually just make my picture bigger right now. I'm not gonna. But I also think it's super cool to show that, how talented you are. I mean, I know people don't think much of this, but seriously, erasing the T and writing the S and T all while talking. Here, watch it again. Just go back until we can see it. Right? Oh, that's maybe right there. Right there. So here it's spelled wrong. Spelled wrong right here. So let's listen and watch.
For each of these, okay, our net force is going to look like D, C, B, A. So then the question becomes, what's causing that net force? Why are these things accelerating, specifically B, C, and D? So you likely kind of have in your brain something about the force of gravity causing those things to either move down the inclines or move straight down. So what's causing that?
By the way, this idea of having some things sort of pre-written and below the screen, right? So as she's scrolling, it's like, whoa, hey, here's some new information. One of the questions that I always think about is, do I want my students' notes to look like mine? Right? And so I talk to a lot of people about this idea, like if I want my students' notes to look like mine, A, I could just provide it to them. B, I could not have anything pre-written because if I take the time to write it, that leaves them the time to write it. But if we don't want our students' notes to look exactly like ours, what do we want their brain doing? And there's no question that we can read this, in 0 seconds flat, right? And get our brain ready for this new idea. Now, having it below the screen to scroll up and sort of reveal is super smart, because otherwise, someone like me, I'd just be looking down the whole thing, trying to read the whole thing. We can get a clue about how much there is based on the scroll bar. OneNote tends to have a default file size, which can grow if you write some more. So it's possible this is just the default, but it's also possible that this is telling us that we're about, what is that? A quarter to a third of the way through these notes. So that's really interesting.
Net force? Well, the force of gravity. Now, in B, the force of gravity, remember, is pulling straight down. So in B, only a little bit of gravity is going to pull us down the incline. In C, a little bit more gravity pulls us down the incline. And then in D, gravity can put us right into free fall. So in all of these, it's the force of gravity that's causing us to accelerate down the incline or straight down. So that's going to play a role when we get into inclined planes. So with inclined planes, we normally have a situation like this, where we're on a nice flat surface. This is what we're used to. Okay? And our coordinate system is x direction is horizontal, y direction is vertical. Now, when we incline our surface, because that's what an inclined plane really is an inclined surface, our coordinate system is going to kind of tilt right along with it.
Cool.
So our coordinate system tilts right along with it. So we have still like this kind of up and down, but it's at a diagonal, and this side to side kind of at a diagonal. Now, we don't really want...
So I'm watching to see if she calls those x and y, or x prime and y prime, or if she wants to reserve x and y to mean always horizontal and vertical. I think these are the tough decisions that you can make, or your textbook authors can make. I think that the idea that that these are the two directions that matter, and so we're going to do our analysis here, even though we know, for example, that the force of gravity is always going to be along this y, so maybe that should privilege this. So, right, do you privilege the physical motion, or do you privilege one of the dominant forces? And of course, we all know you can do these problems either way. And so I think I may have paused right when she was going to say something about whether we would call this x and y. So I'm just going to back up 5 seconds and listen to that whole sentence.
And this side to side, kind of at a diagonal. Now, we don't really want to call those directions x and y because x is synonymous with horizontal, y is synonymous with vertical. So when we're on an inclined plane, the directions that we deal with are parallel, meaning parallel to the incline, right? And this system, that symbol there means parallel. And then we also deal with perpendicular to the incline.
Cool.
Right? So this direction is perpendicular to the incline because it makes a 90-degree angle with the incline. And then this is parallel to the incline because it's right in line with the incline. So when we are thinking about forces, we want to think about, are they in the perpendicular direction, the parallel direction, or maybe some combination? Okay. So here's a box on an incline, and we're going to say that this is a frictionless incline. So I'm going to write mu equals 0.
Cool.
So on this incline, or on this object, we have a force of gravity. And then remember, we're on a surface, so we do have a normal force. And remember, normal force is always perpendicular to the surface. So perpendicular to the surface is along this dotted line. So my normal force needs to kind of point off at an angle like this.
Cool. And that's the real new thing here, right? I think that all of a sudden you have to do vectors, you got cosines and sines, right? They got there are things. This is the new thing typically in a physics course if they've been doing just sort of horizontal things. Now it's possible they've been doing trajectories, so they've already been doing some x's and y's where the x is usually boring. And the y just has, acceleration downwards. But this, it's like, whoa, hang on a second. How in the world does that block stay on the plane if all it can do is move in this direction here? There's got to be more than just this force. And so the old rule of, normal force goes up just doesn't do the trick, although, it's tricky, right? So imagine you said that the normal force was up, because that's what it always does. It just fights against gravity. Then, let's say you've been doing a lot of these horizontal problems and you're convinced, the normal force is just the exact opposite of gravity. It's as though we can solve these problems like they're not in gravity, and then I guess it can just move anywhere it wants. That's tricky, because if you were to give it, in that situation where there's no net forces and then you come in and nudge it down the hill, of course it'll just go down the hill. But it's so tricky when we have these new angles we have to worry about.
So if I think about that coordinate system that we just talked about, we have perpendicular to the incline, which is that yellow highlighted line.
Cool.
And then parallel to the incline, which is that green highlighted line.
Awesome.
Oops, having some issues getting the pen I want. So again, that's perpendicular, that's parallel. So it looks like the normal force is nice and in our perpendicular direction. That's great. But the force of gravity is not perpendicular or parallel. It's a little bit of both.
Yeah, that's the problem.
So what that means is we need to find components
Cool.
of the force of gravity, much like we would need to find components of any force that's at an angle relative to our coordinate system.
Cool.
All right, so.
All right, I think I'm going to pause there. I've gotten a little long here. So this was really, really cool. There's so many things in here that I really, really liked. Just this most recent thing of using the highlighters. Again, it has to do with something that the students might not be able to do. They might not have highlighters lying around, but man, are they useful, right? You can still see the black underneath. It really drives home what it is we're doing. And then this point here is kind of, she's done such an awesome job to build up to this, right? Like, oh my gosh, we got to do some work here. Because there's some subtlety to this. I really, really liked so many aspects of what she was doing here. So I really thought it was great. All right, everybody, I want you to have a great day. And remember, physics teachers are awesome.